Trying to find my screen now. Somehow this never gets easier.
You'd think it would.
Back and forth.
Yeah, finally got it back. I think we got to do it more often. All right, let's get started. So, in our agenda today, we have got a few announcements before we jump into the technical program. Our technical program will consist of Al giving us some observations of the W5HN beacon. Very interesting, on the edge of propagation observations. Have been pretty exciting to follow. And then I'll present the first part of what we're calling automated beacon receivers. These are specially commissioned units that will quietly and effortlessly for us record beacon signal strengths and send them on to the NTMS propagation database. And we've got one with us today. It's here to my right. That's a complete unit, and we're going to turn that on and listen to a 10 gigahertz weak signal. And then I'm going to challenge some of you to come up and peek the dish on the signal using nothing but the feedback of a number, a signal strength number. Well, you won't hear it like usual. You won't see a waterfall like usual. You'll look at a number and watch that number get weaker or stronger and see how to peak it up that way.
How often is that number updated?
It's set in the script right now to update every 1 second. I can probably set it for half a second. And that'll be not as good as an analog needle, but it'll be close. It's just a difference in the mind when you're watching that number. All right, so a couple of the announcements. Bob Strickland, N5BRG, sometimes he is here in the meeting, usually, sometimes in person. And Mott's have donated some gear and some parts, and those are up here on this table. Some of them have already been picked, but if there's nothing in your go-home bag, please come by and pick up something. At least help me throw it away if you're not actually going to use it. Mott's also donated an HP BP20 power supply. If you'd like this unit, please see me. I've got it out in the truck. All right. 220 volt AC input gets you 50 volt DC at 50 plus amps output. And if you look at W6PQL website about the amplifiers, there's a whole bunch of these amps that he sells that use this power supply, all the way from a standalone kilowatt amp for 1.8 to 50 megahertz, and then he's got single standalone amps at 50 megahertz, 144, 222, and 432. Then he's got a 600 watt 902 amp and a 600 watt 1296 amp. So these are all EME kind of strength PAs, and this power supply will power them. And Mott's has reminded me numerous times to remind everybody that he has a complete 10 gigahertz rover and a 24 gigahertz rover system for loan. So if you're thinking about roving and you don't already have one, we can get one of these to you or both of them to you and then pair you up with someone that has some experience if you're unsure. Kent, you have your hand up? Yeah.
He has trouble with walking.
Yeah. Right, so we want to see if there should be no reason at this point that if you want to do some roving, that you can borrow one of these rigs and get out with somebody experienced. If I look around and Al look around and Scott looks around, we really need some new blood pounding the street out there and getting in the rover miles, if you will. If you fast forward 20 or 30 years from now, who's going to be here and what are they going to be doing? So this is a concern. But we do have the equipment, it's ready for loan, and we just want to get it in your hands and get you out there where you can get some experience. You don't have to build your own equipment, purchase this stuff, try to figure out how to hook it all up. If you just want some experience right now, you can get it. I have a little beacon news. Al has a lot to add to this, but basically the beacons that we're going to talk about that are in Burleson, those are intended to move to Denton once we can get access to the Texas Women's University, the dorm building. In the meantime, they're on the air from Burleson. All beacons signed W5HN/B, EM12IL, and we're going to change the sub mode here. So what's printed here will get changed. It says Q6560C. That's going to become 60D probably tomorrow. So we'll communicate that out over all the means that we have. Let folks know that it's changed. Here's some notes for you. This comes from observations. The CW and carrier segment, which transmits on the odd minute, can be found at 1,000 hertz when you're dialed to the frequencies that are listed. The WSJTX sync tone is found at 1,200 hertz. Al has more on that. So here are the three frequencies and the metrics for the units. 10 gig is 1 watt with 40 slot. 24 gig is 1 watt with 40 slot. And 47 gig is 10 milliwatts with a 19 dBi horn. There is a plan to raise the beacons from 30 to 40 feet and add a 24 gigahertz dish pointed to EchoMic 13. That's for you, Keith, and for Al and the others. In fact, the whole reason to separate the beacons from 30 to 40 is to get some pipe up there that we can mount the dishes on and give it a little more height. The last bullet point, there's a plan to add two 10 gigahertz dishes pointed to EchoMic 13 and EchoMic 11, which we believe will help the beacon show up more often than it does today. The path loss is pretty high. Burleson's located a long ways away, and there are diffraction losses from the bulge of the earth and ridges in the way, and then there's just raw path loss. It's somewhere near 240 dB. So if you that do EME recognize that number or a number slightly higher, you'll know that's just about as tough as an EME path without the polarization changes and other problems that you have with EME. Next is a note about 47 gigahertz. We have another 47 gigahertz beacon that's going up into the Princeton area. The grid is located here. And this is supposed to be dropped off this week, so hopefully, weather permitting, this will be on the tower pretty soon. It will be at 47088-353. It'll also sign W5HNB. It has the CW carrier. We'll change it to be Q6560D as in Delta. Runs 10 milliwatts. This one will be on a sector horn rather than the conical horn. It'll be horizontally polarized. Then beacon monitors will need to be built for 24 gig and also for 47 gig. We will be asking NTMS to do some funding for some of that and the research thereof to round out and close this loop on monitoring 24 and 47 gigahertz beacons. So with that, we'll move into technical, and The first one will be from Al. Let me see if I can find that. Reve, right. There.
I've got a USB stick if you want that.
Oh, I've got it here. I just don't know what I'm doing. Like usual. There. There. Now. Can't kill it. It won't die. If you see Al's presentation come up, please let me know.
There you go.
Phew. I know I can never do that again. Whatever it is I did. All right, Al, you are up.
Swap positions.
Yes, and your next slide is shown over here,
Okay.
so you can just click this mouse
Okay.
to make it change.
Am I going out? Probably shouldn't touch anything, huh?
I don't think you're going out full screen.
That's all right. They need to see the presentation anyway, right?
Okay, well, you can go ahead and go.
All right. Well, good afternoon, everybody. Al, W5LUA here. I want to talk about some observations I made on Jim's beacon, which is really interesting in the fact that we have a beacon that's non-CW. So actually, when you record data, you can actually see the swings in QSB and fading pretty well. And of course, you can see it disappear because it does take some enhanced conditions to see this, and we do manage to get some. We didn't get any yesterday, but it was in the aftermath of the storms that we had the day before, at least that we had up by us. So it's just interesting. I've got a ton more data than what I presented here, but I didn't want to bore you too much with WSJT waterfalls and decoded signals. But let's go. Whoops, here we go. All right, here's the path. This is K7FRY. I'm up here in the upper right-hand corner, and Jim's down here in Burleson, EM12IL. That's a 95-kilometer path. And if you look at mid-path, it kind of goes through Arlington-Irving area, almost halfway between Dallas and Fort Worth. So I'm not looking through Dallas. I know other stations like Keith are looking through the Dallas buildings and haven't seen it yet. So maybe that'll improve with more gain down on the beacon itself.
Hang on, Al. Keith, I'm going to call on you. Can you see the K7FRY screen?
No, I got the cover.
Okay, let me get over there. They're not seeing what you're seeing.
Oh.
We're seeing here. They're seeing something else. I've got a monitor there, so I can see what they're seeing.
Now it's going out.
Changed.
See what it says. Okay. Sorry about this. Okay, let's stop that. Let's say this again. No, no, then you got to click this. Want where I'm having the problem is getting the PowerPoint to play. There. Yeah. Now you're good. Now you can. No.
It's not moving from that.
Second.
That looks like the presenter's view.
Yeah, it is. Yeah, and there's such a long delay here. So they're going to see this now. It just takes it several seconds,
All right, we'll go forward then one.
and then it'll take a few seconds.
Okay.
All right.
All right, so now you can see the math presented on K7FRY. I'm in the upper right-hand corner, and Burleson's down in the lower left, and it's about 95 kilometers or 59 miles. Let's see if we can move forward from here.
Yep.
Oh, yeah, we're moving forward. Okay, here's the beacon built by Jim that he was referring to earlier. The whole beacon assembly sitting up at 30 feet right now in his backyard, and uses 40 element slot arrays, as he mentioned, on 10 and 24, and the actual horn for 47 gigahertz is looking out through this little window here. If you can see my cursor going out, probably not.
Probably not.
Okay. In the lower right-hand corner of the middle picture, you can see the window for the 47 gigahertz. Oh boy, why are you going that way?
First is okay.
Moving forward, this kind of represents the 10 gig beacon. That's what I'm going to be referring to here. It uses an RF0 up in the upper left-hand corner, around a couple hundred megahertz. And we're heterodyning up, because I was asking Jim about this, because you can multiply with the RF0. You can say that we're going to multiply times 96 for 10 gigahertz, and it'll spread the tones out, or I should say shrink them up, so that when you multiply it times 96, it still is, Q65, 60, C, or D. And the only downside with doing that is, he said the sync tone was kind of, warbling back and forth, if you will, or wobbling back and forth. So I guess it has to do with the way that the RF0 is disciplined. It's just not the right way to go. So that's why Jim chose the approach of using a VHF signal out of the RF0 and then heterodyning it up. So he does that with the mixer there in the green, the demi-LO in the lower left-hand corner. And now you got a signal at roughly 3 gigahertz, or 1/3 of 10368, and you run it through a Paul Wade multiplier board that amplifies and multiplies, generally with some mimics. And that's at the 10-watt level, and Jim was using a 1-watt PA to get the level up higher. So it's running 1 watt to 40 elements. And here you can find this on the paper on NTMS.org. Now my station, I got to admit, it's kind of antiquated. It's been up there for years. I used to have a preamp up there, and I don't anymore, but it's a 2-foot dish at 70 feet, and it's actually a converted surplus dish, and I'll bet it's been up there for 25 years or so. I used to have a preamp up there, but either got zapped by lightning or filled up with water. So I haven't been using that for the last several years. And I'm also doing something else different. I'm using EW63 waveguides, similar to this stuff right there. And it's slated for 6.4 to 7.1 gigahertz. And I used to run this on 5760 in the past, so that's why it's 6 gig waveguide. And I remember, it's been years since I looked at it, but if you compare the loss of 80 foot of EW63 at 10 gigahertz versus 80 foot of EW90 that's slated for 10 gigahertz, it's lower loss than that. Now, they say that when you start to go above the cutoff frequency, that if you're trying to get a wideband a signal out with very little phase variation over the band, you don't want to use EW63 at 10 gigahertz. You'd want to use the EW90. But it's actually about a dB or two lower loss than EW90. And I got to admit, I do evacuate it. Well, no, I don't evacuate. I pressurize it with name brand Walmart aquarium pumps. And I blow it through dry air. And that's how I try to keep it pressurized. But it's not perfect. I watch my SWR, and it varies a little bit with time of day and relative humidity, yada, yada. But it's the system works. It's worked 1,600 kilometers on 10 gigs, so I can't complain. I do have a 1 dB noise figure in the shack and a Flex 6600 at 29 megahertz. And I use 29 megahertz as an IF on the microwave band just so I don't see crosstalk from 2 meters and anything else that would convert down to 28. So that's why I'm up at 29. So it's a dated setup for sure. Okay, like Jim was saying, if you're going to listen for the beacon, it's on it's 0 beat 10368.370. So if you go to 10368.370, you won't see the sync tone. You'll see some of the tones as they go up, but you got to get them up higher in the band. So we'll set the receiver on 369, 10368, 369. So the CW ID and or CW ID and the keying line will be at 1,000 hertz, and that's easy to see. And if we're using Q6560C or D, that sync tone will be at 1,200 hertz. And you're going to see that way before you start seeing all the individual tones. And you do need sufficient bandwidth. And, with a lot of the radios today, it's pretty easy to get. My Flex is pretty flat, and I'm sure most of the SDRs are. But I think back of my IC271 days, it had what appeared to be a 2-pole filter. It was a dip in the middle of the band. Well, you don't want that for this. And I don't know how some of the other rigs are, but you need to have flat bandwidth. And in the appendix, you'll see a write-up by DL3WGG about flattening it. It's just a WSJT feature. It's probably mentioned in the handbook. I probably looked at the handbook more in the last week or so based on our discussions than I ever have. But it's I'll show that at the end. So moving on, we're working with the 60 second periods because, like Jim's mentioned, we're going to be transmitting the CW ID in odd minutes, and the even will be Q65. Now, if you go down to 30 or anything else, then it becomes a little bit harder to remember. So I think it's good that we stay with the 60 second. And if you look over at the different modes, the C and the D modes are ones that we use on the moon, like on 1296 through 10 gigahertz. And predominantly 10 gigahertz uses 60D because it's spread a lot, and because of the vibration of the signal bouncing off the moon. And I've also made 10 gig range scatter contacts using Q65D, and I think it's a good mode to stay with. But the test I'll show you here will be some results of some of the 60C and 60D decodes. So like I mentioned, we'll show some decodes on C and D, and then some other interesting observations, because when you're looking at signals, you like to look at reflections and and stuff like that, and it's just kind of nice to have a beacon that you can look at. And what's really nice is you can quantify it, at least by decoding the digital portion of it. So the first time I tried this was on June 29th. Jim started out on 60C. And so I'm on 10368.369, submode C, and we're 62nd. And I finally went off and generated a WSJT, I guess the program or subprogram for terrestrial, because I have a problem. If I go between terrestrial and EME, I got to go back into the advanced settings and get rid of decode after EME delay. I don't know how many times I've screwed that up, being on terrestrial and being set up for EME. And if you're off by 2.5 seconds, you're not going to decode. You're just not going to decode. So I individualize this for terrestrial work. So, but what I was really surprised at, how few single period decodes there were. You can see there's only like 3 of them here, and there were a lot of average periods going on. And as Jim kind of explained to me later, you can see that like Q03 means it used 3 periods to decode or average. And you can see this one here's another 3, here's 4 and 6. But the signals here are in the -23 to -25 dB range, and the noise floor is like -27 or so for this mode. So we're not too far above the noise floor. And I was surprised that most of them were average, because on the moon I don't get a lot of average decodes. It just seems like it's the single decodes is what comes through the most, and maybe some -30 decodes I might have seen on the average, but generally we don't need it. But we're working with signals here that most of the time they're not there anyway. So we would like to see it as soon as they pop up out of the noise. So I convinced Jim to go over to D, and I don't know if the propagation improved, but it might have. But now I seem to be getting a whole bunch of single line decodes, and only a couple average. And I'm not sure exactly why that is, but the signals are they're considerably stronger, so -18 to -22, which are pretty good signals. The average were 23 and 24. But I guess if it's getting a lot of single decodes, it probably doesn't waste its time with average.
Right.
I'm looking at Jim on this one.
Better propagation.
Yeah. So, but that was interesting. But also, just to look at the timing, these were like a 13:30 to 14:30. So we're talking about 8:30 to 9:30 in the morning. And most of the times, I don't get up that early, so what it was doing at 6 in the morning, I couldn't tell you. But I've left it on overnight and looked at it the following day, and most of the peaks are mid-morning. So we'll call it 9, 10, 11 o'clock. And even yesterday, it came out in mid-morning and went away by 4 or 5 in the afternoon. So it seems to like the drier part of the day, at least on 10 gigahertz at this distance. Now here's a look at the waterfall. And you can see that you probably cannot see it too well, but the first sequence up here in the waterfall, that's an even sequence. This is an even, well, you can't see that either, can you? You can't see my pointer out there, right?
Right.
Well.
I can see it, Al.
Oh, you can out there in the audience?
Yes.
Okay, good. Yeah, the first one up here is an even sequence. Then it's odd because you see the carrier, and then even with the WSJT, and then odd. And these two signal levels here are -18, -19 dB signal to noise ratio. And if you look at it, it's pretty easy to spot the carrier, and it's down in dB from the tone because the tone is constant. And here it's a sync tone and then a bunch of other tones going all the way out over about 800 hertz, which are kilohertz. Hertz. Going out about 800 hertz for Q6560D. And also, when the WSJT is done, at the end of it, there's a little bit of carrier going out. And then when it starts the odd sequence, it's a CWID, so it'll be W5HN/B and EM12IL. And I normally don't turn up the volume. I turned it up a little bit today, and could actually hear some of the tones kind of dancing around in there. But these are pretty weak signals. Oh, and also, you don't, let's see, you don't see it here because it hasn't completed. I should have had a shot of seeing the sync tone kind of peak up down here. Because as soon as this gets done decoding, that even period, you'll see down here, it'll be a peak, and that peak is where it found the sync tone. So if you can't see it up here, if it's not plainly obvious like it is in this waterfall, you get some idea on this curve down in the yellow curve down here where the peak is. But I generally don't even look at that because the sync tones are pretty obvious. Now on July 3rd, let's see. You know, this is probably typical of the levels. You were talking about 14, 1500 in the morning, you know, 17, 18 dB. I've seen some signals decoded down at minus 27, but never anything further than that. So I really think it confirms, you know, when it disappears, it's below minus 27, which is the theoretical noise floor of the modes. What I found interesting was the noise floor says is the same between Q6560C and D. And I would have thought, since the one used more bandwidth than the other, that it wouldn't be as sensitive as the one over the narrower bandwidth. But you always learn something new. But the noise floor is about minus 27, and only with averaging would you possibly see something lower than that. And I have yet to see anything lower than that show up in the average, but time will tell. And here, this was an interesting morning. You know, most of the other mornings are pretty constant, within 2 or 3 dB. You know, very slow fading. And this particular day, I was really surprised at the variation. And if you look here at 1240, it was a minus 8 signal. So this right here is a minus 8 signal, and you can see a lot of the tones really well. But a minus 8 signal on the moon is a pretty good signal for a small station. But then you go 2 minutes later, and it's minus 19. This one in here is minus 19. It's 11 dB fading. That's the first time I'd seen that, and I'm not sure what was causing that, but some turbulence, if you will. But, you know, it'll decode a minus 19 signal, but all you're going to see is the sync tone right here. And when you're doing EME, this is all you're going to see. We don't send out continuous tones like this over here on the left, unless we're doing CW, but this would be typically what an EME signal would look like, a nice one.
Al, at the very top of the waterfall, is that some spreading up there on
this?
Yeah.
Yeah, I think if I had let this go further, I think that's just a stronger signal.
Okay.
Yeah, it looks like the next period would have been a little stronger. And I would imagine, well, no, let's see, what was the next period is minus 12. So I think it shows that between 1240 and 1242, there may have been a stronger signal level when it was sending out the tone. But there's just a lot of fast fading on this particular day, which is unusual, but it's nice to see it. So here's some other observations. I've seen broadening on signals, and this would be a 60D signal that was not decoded at all. But you look, I don't know if you can see this in here, but around 1200 hertz, that's a pretty wide sync tone. This is a pretty wide sync tone, and probably it may have needed 60E for that matter. I don't know. But I've noticing that, and then also here is some widening in this area, but it could also be aircraft scatter, just slightly moving off. And but when we're shooting across Dallas, if you will, or the mid-cities area, so there's a lot of moisture out there, and a lot of effect from the buildings, and it's really kind of a rough path. I think 59 kilometers in the clear would be a lot better than 59 kilometers or 95 kilometers going across Dallas-Fort Worth. Now here's an interesting plot. The top one here, that's the Jim's Beacon. That's the strongest I've ever seen it. You know, it's like 12, 15 dB out of the noise, and that's it right there. And 10369 is right here. And this is the HN Beacon out of Denton, which, by the way, if you listen for it, its frequency varies as it has for years. and right now it's stuck key down. I tried recycling the power, but the keyer is kaput, and we're trying to get up on top of the dorm to pull it down. And if we do get up there, we're going to pull it down to work on it and maybe upgrade it. So, use it while you can. And then one day I noticed this was happening. Actually, the two beacons collided. And, of course, you can see Jim's beacon, very stable, GPS locked, so forth. And the NTMS beacon is just kind of sliding right on through. And this is in the morning. Temperature's rising as time goes on, so you can see it's moving higher in frequency, and I've caught it coming down in frequency. So it provides QRM twice a day. And I think you'll see a lot of that this coming week with our triple digits. And also you can see down here the yellow curve I'm not sure what it got that off of. Disregard that since we had QRM. All right, now there was a thunderstorm located in EM12OS. The tops are only at 24,000 feet. And I thought, well, why not try to listen for it? Jim's omnidirectional, and so I aimed right at this thunderstorm. And if you squint hard, you can see, I see it because I want to see it. Now, the odd sequence, so here's the carrier. It's spread right there. Even, you can see the sync tone spread there and a little bit of spreading here. So maybe look at it at an angle. Anyway, I saw it. Jim saw it too, so it's got to be real. But anyway, just interesting things you can do with a beacon, and especially when you can quantify it, the signal strength. So having a beacon based on the RF0 bore, as Jim's been saying, is certainly the way to go for a microwave. We got to heterodyne it up. Unfortunately, our beacons right now on 3 gigahertz will be GPS locked, but the 2 gigahertz and the 5 gigahertz and 10 gigahertz are all DB6NTs. And if we try to use the RF0 down at 100 or 200 megahertz and multiply up, I'm not sure about the stability of it, if you will. And we also have to use a different RF0 for every band because they don't all start out at the same frequency. If you use an RF0 at 200 megahertz, we can just heterodyne each one of them up. And, that's really the smart way to go. And so we probably would consider that. But getting, quantitative data out of this, I got all sorts of screenshots and I sent them to Jim, and he wants some more data on the actual wave files. So I've been trying to keep all the wave files. I got to keep an eye on my hard drive because, boy, it'll certainly populate it with wave files. But so far, so good. And I made the comment to Jim here, I think we should stay with 60D because, we have a lot of rain scatter potential with the guys up north. And D would be the best approach for them to actually decode the beacon. And I think that would be the challenge, is to decode it. But I think no matter what, hopefully we get the beacons back up at TWU, but there's a 3-watt demi-amp up there right now that we would take off the present beacon and add it to the beacon system that Jim has generated. So, yeah, I think some of the guys up north could, yeah. And the same with K5DOG's been monitoring both beacons. I think he's only heard the Denton beacon. Steve hasn't heard yours per se.
He has not detected it yet.
But he's really excited about, having something to play with, the beacons and all that. And of course, Steve, K5MNZ, did I have that right, Steve? Sorry. Has been looking for the beacon as well from down south. And that's what path is that to Jim's? What's the DX?
He actually detected the beacon. It was 98 kilometers.
No, mine is. Oh, his is closer.
It's closer than.
See something.
Okay.
Is it closer than 98 kilometers?
I think it is.
Yeah, 105, wasn't it?
Yeah. So anyway, it's making some progress, and thank you for your work, Jim. Moving forward, this is, oh boy, I'm really nervous with this. I put this in here. A couple of people have been asking about it, and I think if you do this, you can get yourself a flat passband response. And you need something like this. Well, right here. This is fairly flat in here, so it doesn't make any difference where the signals are. You should be able to decode them just as easily, no matter what frequency in the IF they were on. But this is a procedure that Charlie Suckling came up with, and it's basically he's saying use a receiver bandwidth suitable for the submode. So basically, you need to have something that's capable of probably at least a kilohertz for the Q6560D, and that's not a lot of bandwidth, and it needs to be flat. You can't get any more bandwidth out of this approach than you have bandwidth a capability in the IF and the radio. But especially if you move on to Q6560E, which we've done some of that on the higher millimeter wave bands, then that's really important. We're still good here, Jim? I guess yes, we are. So the procedure is, this is all on the WSJT form or WSJT screen. You have to have flattened checked, and then you erase the reference spectrum. If you may not have had one, but just erase it, and you're starting out from zero. And then you push the button under Tools that says Measure Reference Spectrum, and basically you let that run for about a minute, and just so it does a nice job averaging, and then you stop it, and then you click Reference Spec, and it should flatten out your passband response, and it'll look hopefully similar to what I was showing you there. He uses Audacity. I've played with that a little bit, and I'm sure some of you have more experience with it, but I think he uses that to really be a test as the flatness of his passband. And, like mentioned earlier, it can help in the decoding of very weak signals. That's all I had.
Any questions for Al?
Oh, I think I somehow got you out of that. Well, here we are. We're still okay.
Okay.
All right. Thank you.
Thank you, Al. All right. As I'm trying again to get this to work, how many folks are Raspberry Pi hobbyists here? 1, 2, 3 and a half, 4. About a third of our audience. So the subject that we're going to come up with here now is about the beacon monitors. That is, if I can get things to work. So. I guess part of the rehearsal for getting ready for this meeting is to spend an hour just making sure I know which buttons to push and get this to go, which I'm remiss in doing. Now, I want to take a break as soon as we introduce the ideas of how the beacon monitor reports its data, finds its data, and then I'm going to ask you to come up. Maybe Al would be our first volunteer if he's still here. I know he has something else going today that he has to attend, but I've set up a beacon monitor right here. This is our first prototype, and it's ready to go. It's ready to be deployed to one of several locations where we have volunteers that said they would take it. And I've set up a weak signal source at 10 gigahertz, some dozens of feet back. It could be a half a mile away for all intents and purposes. But I want you to monitor the output of the beacon monitor, monitor the output of the beacon monitor, or observe the monitor's output, and try to peak this dish on that source back there by looking at a number that's going to print. Okay, so let's get going. So this is a new journey. I've drawn the vortex, which I've been swirling around in for a while. Al's been down in there too a couple times. Mostly I'm drowning in research and information and many, many hours in my Claude account, debating a number of different things and coming up with what you're going to see here. And so the first question comes up, well, why do we even need them? We have Al, the supreme beacon monitor, because nobody will ever be able to replace the human element of, hey, I'm seeing a trace, I'm going to adjust this, I'm going to do that, I'm going to tweak my antenna, now I can get a decode. Those are things that a person can do, but it's just one person, and it's one person in one place. So as great as that resource is in the way that he uses his system, automated beacon receivers can be deployed in various locations, and then they just quietly report the strength of the beacon. What would they need to do? We'll talk about that. Can they be made at a relatively low cost? Very key question. Everything costs so much nowadays. And then finally, if we make one, how do we calibrate it and test it? So here's some of the why. Where we were a month and a half or 2 months ago was we knew that we had this great propagation analysis tool that had perfected algorithms through artificial intelligence interactions. Graham and I had worked this up to a point where we had a pretty significant investment of intellectual property and infrastructure. There's several servers involved to produce this information, be able to extract the other tooling from the sources and build and keep it active, keep it current. We started by examining about 80,000 actual microwave contacts. Those came large part from the ARRL 10 gigahertz and up contest results. And then we still get link closures, is what I'm calling them. In other words, either contact logging from hams that are manually logging into this tool, but they're at a very, very slow rate because they require a manual submission. They require you to go to this website, input these fields like you're capturing the data in a log. Why do we need the monitors? We need it because additional real-time path loss and gain is needed. We need it for different seasons of the year. We need it for different geographical areas. And a monitor can measure and report results tirelessly, hour after hour, day after day. Here's another on the why slide, and I want to just take a minute. There's a name that you'll recognize here. But Jacqueline Bell Burnell was running a continuous automated chart recording, monitoring this radio sky for scintillation studies. Buried in miles of pin chart output was a repeating pulse signal that no human observer would have ever caught by spot checking. It only showed up because of the instrument never stopped listening. It was just a dumb, continuously running receiver, and it caught something. The next bullet point, Joe Taylor and Russell Hulse discovered the binary pulsar in 1974. Its name is there. The Nobel Prize was awarded in 1993, almost 20 years later, but it wasn't for the discovery of the binary pulsar. It was awarded for the years of precise repeated timing measurements of the pulsar's orbital period, which showed the orbit decay at exactly the rate general relativity predicts for gravitational wave emission. So it was their recording methods, it was their diligence to maintain and the discipline to, I'll use the word ingest and quantify that information that won them the Nobel Prize. I don't think we're going to discover pulsars with our humble beacon monitor, but just as Al has said, some things happen. There's strange things happen. He went from, he had an 11 dB shift, I think it was, in 2 minutes. As we perfect our tools, we might be able to explain that. And it might not be interesting to anybody other than us, but it's still a discovery, it's still a quest, it's still something worth doing, in my opinion. What do they need to do? They have to monitor a specific microwave band. Was there a break in there?
Yeah, we're not seeing the presentation, or at least I'm not.
Oh,
out here
that's
doing
not good. What'd you say, Kent? You'd like the floor for a moment, okay? Well, I'm glad you broke in and told me it wasn't going out. I'm not watching my own monitor. Okay, now you should see what do they need to do. Do you see what do they need to do?
Yeah, it's there now.
Okay, I think that was a yes.
Yes.
Okay, what do they need to do? They need to monitor a microwave band. None of the SDRs have a wide enough bandwidth to monitor 2 microwave bands at the same time. They can't even do 2 HF bands or 2 VHF bands. They're not that wide, not the ones I can afford are not that wide, but they could monitor more than one beacon on a given band. They need to be located such that a beacon can be detected some percentage of the time. I'm not sure what the percentage is, but you don't want there's a little value in a beacon that is monitor that's 100 feet away from a beacon. There's some value because it detects RF, but we could put an RF detector in the beacon and have it where we could pull that through our hologram shield that we have to work remotely with it. You want the beacon monitors to be placed at not necessarily the edge of the propagation like where Al is, but somewhere where the beacon can show a fluctuation. I've got some suggestions for that from my own observations with that unit. The reports need to be centralized into a database. We already have the propagation engine, and there's other web accessible pages possible where you can display the real-time path and prop status. You'll hear me talk about ham SCI. How many of you know what that is? Ham SCI, Science Contribution. Okay, so we'll talk about them because they have begun to collaborate with us from the University of Scranton. Very interested in what we're doing. We're interested in what they're doing. Can it be made at relatively low cost? Well, now, here's where the good news is, in a way. The very first one, this one right here, is made from a satellite LNB with a surplus dish. The satellite LNB is a $15 unit from Amazon. Drifts like crazy. Although you won't see it so much here indoor in these less perturbation conditions. It doesn't matter that it drifts. Our SDR can find it and quantize the strength. Use a low-cost SDR dongle to process the LNB IF. Use a headless Raspberry Pi to manage the SDR and report the results to the API. And use the existing Wi-Fi router at an ops QTH for reporting back to the database. Here's the way that looks. So you got it's sitting right here. You've got the LMB in the dish. You've got a bias T to power the LMB. It needs 12 volts. Moving to the right, you've got the SDR, then the Raspberry Pi. In this diagram, there is a Wi-Fi connection. You could make this an Ethernet cable that runs over to the Wi-Fi router, and then that would provide the route for the Raspberry Pi to send reports to the NTMS database. You'll need a 12-volt, 5-volt converter for the Raspberry Pi. It has to be capable of 3-amp power. I got in trouble trying to use one that wouldn't quite go to 3 amps. It's definitely need to be 3 amps. Here's a model number 2. This would cover bands below 10 gigahertz. So for the sake of ham SCI's plans, which are VHF, they want to watch 144, 432, and 1296. This kind of idea would work. You could use a hack RF or a Pluto. Well, in fact, you could use the SDR RTL dongle all the way up to 1296. So I don't want to leave that out. Up to 1296, you don't have a very expensive SDR. Again, you use these same components for Wi-Fi reporting, and that could be an Ethernet cable as well there. Model number 3, this would use existing equipment. We've had a couple people say, hey, I wouldn't mind using my gear to do reporting for you. Obviously, you can't let it sit here and do this forever, but this setup is not what Al's doing. Al is using his own equipment, but he doesn't have the Raspberry Pi and the automatic reporting feeding the propagation database. He's doing manual visual assessment and data acquisition, and then sharing that with it's been very key to what our understanding is up to this point. Finally, this is the high stability version. This would enable WSJT XD code, and it entails having a LNB that can be disciplined by an external GPSDO. And here are those again with their pros and cons, kind of what bands they would cover. Here is the components, because I'm going to build this one, maybe not next, but soon. This is the high res, so this is using the bullseye down here in the lower left that has the tap, the red port on it. Some of you know this. I'm sorry to repeat things you already know, but that red tap F connector connects to a 20 megahertz TCXO inside the unit. So it's a tap to let you take 20 megahertz out. But what we do is pop off the TXCO and then input 20 megahertz there. And our 20 megahertz would come from the Bodner, which is programmed to 20 megahertz by us and is therefore GPS disciplined. So now we have a locked LNB feeding, you've got to have your bias T, and then you go right into this SDR dongle at roughly 618 megahertz. That's the down convert from 10368, and away you go. And this particular Raspberry Pi has a Wi-Fi USB device on it, $8, and that gives it the ability to communicate wirelessly to Wi-Fi. It does, but it doesn't work inside a metal case at all. So that's why we did this. These are the pieces that are going in to a metal case, which will be our outdoor model. And but to your point, the Raspberry Pi has a Wi-Fi antenna printed on the PCB board, and it works fine in a normal scenario. Okay, so to install the monitor, we have to choose a location, consider how it's going to be powered, has to be within range of the Wi-Fi connection or use an Ethernet cable. Indoor units in a plastic case use the Wi-Fi antenna printed on the Pi PCB, but can be fitted with an external Wi-Fi antenna. This unit that I'm going to show here does have the external Wi-Fi antenna, and there's a reason for that, which we'll cover here in just a minute. It's not a metal box, but there's a reason for that. Outdoor units in a metal case have to use the external Wi-Fi. For software loading, I'm going to get too technical here, and I'm just going to fly through these slides because they're more for a very technical group that is interested in those kind of things. If you're just a plug and play, let's get me one of these things, I want to put it in my living room and point it to the beacon, you don't care about this. But the software load, NTMS will perform that. You won't have to do that. We will have to get some kind of a short information form. Now I'm talking to somebody that's out in the Midwest US or California or Tucson or somebody that's not here in DFW. Even if you're here in DFW, NTMS can do that configuration for you. When you get it on site, you have to make sure you can you have a connection to our Raspberry Pi. We will pull the code down from the NTMS GitHub site so we get the latest. We'll run a calibration script that doesn't have to be done because we kind of know what those threshold and gain values are already. We can just plug them into the monitor script. But if we want to run, if you've got a great big dish or some little teeny lens and we need to run another calibration to get the noise level figures again, then we have a calibration script that can be run. Once we get the calibration run, we update the monitor script to use the gain and threshold values, and then we start the monitor. And then we validate that the beacon is being received. The calibrate code does things like over here, how long to dwell per gain step. Well, back up. We're going to flip this slide to here. We're going to go through on the calibration and look at every gain step that's available in the SDR. So now remember, you got your LNB on the dish. It's got a fixed gain and noise figure. It's fire hosing RF into the SDR, and the SDR has 29 different specific gain steps. So the calibration script is going to stop at every single one of those gain steps. It's going to take an FFT sweep. It's going to average the power. It's going to compute the noise floor as median power across the spectrum centered on the beacon frequency. Look at 500 kc each side. It's going to print a table. It's got these columns in it. Gain in dB, that's what it's forcing the SDR to have. The noise floor in decibel full scale. We'll talk about what that means. That's not signal to noise. It's decibel full scale. And the delta from the previous step. These are meant to identify the knee, recommend the gain and threshold. It also creates a CSV file for comparison across stations. Now just a moment on this slide, what is a dBFS? This is decibels relative to full scale. It's not an absolute physical unit. It does not equal watts or volts at the antenna. It's just a statement about how loud a digital sample is relative to the maximum value the file format can represent. For 16-bit PCM audio, which is what all WSJTX WAV files are, the full-scale reference is the largest representative sample value, 32,768. The formula used is dB full scales equals 20 log 10 RMS amplitude divided by 32,768. 0 dBFS is the ceiling, not a target, and RMS versus peak matters. So the RMS calculation, I have it here in a note. That is, I can't read it for all the participants covering it up here, but it's square root of the measurement. I can't read it all. But anyway, there is a difference between what RMS is and what this peak signal is. It's a property of the digital recording, not the RF signal. There is relativity involved here, and I've got some charts here later that try to show, I took it out in a field and it measured on the dBFS, it measured this number, and on WSJT it measured this number. But they don't tie cleanly at all. It's not that pretty number that we'd really like it to be, but it is a relative number, and the stronger the signal, the lower the negative number, the closer to zero it will be in this world, and the weaker, the larger the negative number as it gets further and further away from the zero full scale. Here's what the cold sky measurement, it's just this unit pointed up. Here's some calibration results. I'm not sure what I'm believing about this, but this top, I mapped this in Excel, and so this top slope is the gain values that the SDR was programmed by the Raspberry Pi. So Raspberry Pi said, start at 0, give me 2 seconds, let me look at the noise for those 2 seconds, record that noise. Now, go to the next level, which was 0.9 dB gain. And it said, okay, dwell 2 seconds, let me get the noise, got the noise. The noise was negative 64. It said, go to the next gain level, 1.4 dB, dwell 2 seconds, let me characterize the noise. It's minus 63. So, for half of these values, as the gain went up, the noise level went up. Then the noise level took a hiccup and went flat. Anytime I look at graphs like this, I think of compression or saturation. Something reached a point and that was it. But I still don't understand why, when I go out there and actually use this to listen to beacon signals, that the higher my gain value setting is, the bigger the signal is. And I haven't done what you will ask me next, or someone would, is have you put it all together where you can look at, maybe even 2 signals, a strong and a weak one, as your gain is going up. What's happening are the phase noise skirts and shoulders from the strong signal raising the noise floor? Is it starting to eclipse the weaker signal? How close is the other signal? Is it within a few kilohertz? Is it 100 kilohertz? So, all those kind of things still need to be done. But there is a result here. It did result in giving me a recommendation. I'm going to play this, although there's no audio to it, and I'm only going to play a few seconds of it, but here is the command given down here at the bottom. It's been given to the this device here, and a beacon monitor, and it says, I want to calibrate. And so this last line, you can't read it. It says, point to the sky, cold sky, and press enter. And now here it will start chunking these every 2 seconds. It will start giving us noise level meetings, dBFS, as the gain is raised, one step after another. Now these steps are specific to the SDR. They are put in there by the manufacturer of the software. Somebody here might be smart enough to tell me, but if one of the steps is 20.9 dB, published by the manufacturer, if I just put in gain of 20, because I can put in a whole number, does that mean it goes to the nearest one that was created by the manufacturer? Or does it go down to the next lowest? I don't know. But these are specific values. It's got 29 of them, and it will sit here and it will just go through all of those. And when it's done, let me see if I can advance the video. When it's done, it will come up a report down here at the bottom, and it'll say, here's what we found, here's where your gain needs to be set, and here's where your threshold needs to be set. Yes. Yes. They have different ones. Now, if you use SDR Angel or Flex Radio, or you use a client, it's going to have a gain slider on it somewhere. And when you slide that, I've never looked to see if it's jumping from 20.9 to 31.6 to, if it's jumping to the defined gain values that's in the SDR I've selected in my configuration. or if it's just 20, 21, 22, 23, 24, 25, 26. I don't know. I don't think it really matters that much, but it's just an interesting, what do you mean it's got specific gain values? Yep. All right, and here's some more shots of that to bore you with. Now, how do you connect? We're about to do the demo, but I wanted to get to this point. Those of you that are Raspberry Pi folks know all of this, but I'm operating this device in a headless environment. So there's a Raspberry Pi inside that plastic box, but there's no screen or keyboard inside that black plastic box. It's headless, which means it doesn't have those peripherals attached to it. The way you get peripherals, if you need them, and we do for this demonstration, is we have to all connect to the same network. So I turned on my hotspot on my phone. I connected this Toshiba Toughbook to that hotspot, and the Raspberry Pi was pre-configured to connect to this hotspot because I've had this out in the middle of the country. There's no Wi-Fi device out there, so I have to connect everything through one network, and that will be my phone. You might find that interesting, you might not. But anyway, that's one way you can do it. Obviously, if you're at home, if you're at Al's house, where he's on his Wi-Fi, he may be wireless, he may have an Ethernet cable, but he's on his Wi-Fi, because that's how he gets to the internet. His beacon monitor in the backyard can access that Wi-Fi wirelessly. And he's good to go. It's all on the same network. He could actually SSH into it. SSH is our code for get into it, log on to it. So this Toshiba, I have logged on to it just before Al's talk was over. I logged into this device, and you might have saw me go put it on the power, and it came up and it attached to the phone's network, and the Toshiba is attached to the phone's network. So we're all in the same world now, and I started the beacon monitor just to make sure it would start, and it did. And so here in a minute, I'm going to ask you to come up. Maybe we'll use Al as a guinea pig and try to peek this dish on the weak signal by just looking at its output on that screen. First, let's cover this and then we'll stop. These are the options. For a headless operation, you can use something called RPI Connect. This is the official Raspberry Pi company. You create an account there. It's free. You register your device, and then on your internal network, you can see it, and you can connect to it, and you can get a beautiful dashboard and a screen, and that's your Raspberry Pi talking back to you through this website. So there's a kind of an easy way to do there. On your internal network, everything's connected together on home Wi-Fi, so it just works. And in the field operation, as I said, we use the cell phone. There's other options. There's a thing called port forwarding where I could connect to my home Raspberry Pi from here and control it. And then all else fails, you can add a monitor and a keyboard. That's the oh shit thing, where you've wiped out an SD card or something's really broke so bad you can't get to it on the Wi-Fi. There's the Raspberry Pi Connect. You set it up, your devices show up. I didn't hear you, Eric. Well, we're using a 4. It's highly underused. A 3 would probably be fine, but we're using a 4 for expansion purposes. We're gonna build one that decodes WSJT, and it's going to use a little bit of the horsepower, weenie power, whatever's in there. You can open a remote shell. Here's a remote shell, and you get in this world. Here I've asked for the last 5 rows out of the log just so I can look and say, it's running, in case Al asked me. There it is. I can see the signal strength. This is that Raspberry Pi Connect, and you can actually open up a desktop. This is your Raspberry Pi somehow showing you a desktop. It's got menus. You can open those menus. You can look at the files. You can look at the log file in there. You can always use the CMD. You know, you can type in command on Windows, use the command terminal. I use this thing called Termius. I really like it, and I'll tell you why. Here it is in use. You know, and it's Linux, so you either love it or hate it. Here it is again in use. Looking at a shell script here. Here it is on my cell phone. And so there's HTOP on the right. So some of you know what HTOP is. That's showing all the working processes that are on the Raspberry Pi. All this over here on the left, these are my different connections. So I got a connection whether I'm, on Raspberry Pi 1 or Raspberry Pi 2 or Raspberry Pi 3, or I'm out somewhere on my iPhone. I got all those connections, and they replicate. They go from laptop to laptop. I've got 2 laptops that have Terminus and my phone. And all of these connections all go everywhere. Not only that, the history of what I have typed in. Anybody love typing in Linux commands? No. So all those little long slash this, slash that, backslash this, slash, dash, dash. All that stuff, all that history is kept. And it replicates across all of these. Plus they got these little videos where you can call it up. See over here in the lower right, you probably can't read this, but here's the history of my commands. So there's the history of my commands. So before we get into this, we'll take a break. I'm actually going to demo something here where I've got 2 47 gigahertz beacons being recorded at the same time. And you'll get to see both of those signals showing up in the beacon monitor, but only see one of them at a time in WSJT. And I'll move from one beacon to the other. You can watch them both be decoded. It's about a 5-minute long video. All right, so before you eyeball this for the first time, when I started, it's going to start running, and it's set on 1 second interval. So it's going to look, and then it's going to pause for a second, and then it's going to look again. It's going to print these values. Print. It's reporting 3 signals. The number of signals for it to find is a configuration option. You can tell it you only want 1, or you can tell it you want 2, you want 3, or you want 5. And the reason I have 3 is because I wanted to see the noise. I wanted to see whatever the next signal was that it would find. And when it puts them on the screen here, it puts 1, 2, 3. 1, 2, 3. Every second. 1, 2, 3, 1, 2, 3, 1, 2, 3. It prints the IF frequency. So that's around 618 and change. And then it prints the signal level, the signal power level. Who wants to be first? Al, you want to be first?
Sure. Are you transmitting a CW signal?
Nope. It's a steady tone. It's just a digi-LO. That's all it is. All right. Now, there's the strongest signal, marked 1. So they always rank in the strongest to the weakest.
So there's actually 3 of them transmitting that?
No, that's just noise.
Oh.
The 2 and the 3 are noise. The number 1 is the strong signal. And you can see it'll always be this third one from the bottom. See how it's thin and varied as that guy walked by.
Mm-hmm.
And move the dish and see what's the best you can get.
Whole thing moved?
Yeah, whole thing moves.
Elevation at all?
No, I don't think you'll need elevation. Unless we move it out into that field somewhere. I'll loosen it up a little bit where it's not so tight on me. That's okay.
Ten and a half, 10.4.
Come on around a little more. I can see it in there over the steering wheel.
Oh, it's in there?
Yeah.
Oh, down there in that box. Over here. No. I didn't see it.
One of the glasses, if you're more. Oh, here we go. You got a single baby.
He's been to early rating.
Okay. Who has the need? David. You come up.
I know what that is.
Now, I will leave it there. Congratulations, Al.
Thank you.
Best 9.2.
That's all right.
Okay. Is it up here? Yeah, there's a 9. 9.
Right.
You got a 9. All right, your turn. It's a rambling up. Let's shake the dice.
Yeah.
All right. See what you can do. It'll always be this third value from the bottom. Right here. See, that's a 16. Something. 17. This value right here. 15.7, 15.9. That's the signal. The other two are noisy.
My son's in town. I gotta take off. See you guys. Okay.
Al was able to get it down to 9.0. Then we're going to have someone else come up here. You don't count, Kent. You don't count, Scott. Steve, I don't think you count. You guys have all pointed dishes out in the wind and the rain, and keep on coming. You've got a ways to go, David. Yeah.
Well, I'm doing that.
Yeah, go ahead, Kent.
Highly stabilized oscillator that you use to lock up higher frequencies. Okay? This work was, I supplied a lot of the parts, Mott's did a lot of the work. These are 10 megahertz filters that are so narrow, they take off most of your phase noise. 400 hertz. So, some of you got some from me last Tuesday, but I got 4 filters here. Who can use one? Okay?
Come around, swing some more to the right.
That's to make on both ends.
Hey. You moved it about 2 degrees.
One of those square Chinese.
Okay, you multiply it up.
It goes into the transfer.
Okay.
And what does this do?
This thing filters out a lot of your phase noise from the 10 megahertz.
Now, when you get it where you think you're happy you're going to get it, I want to open up the elevation. Now, don't let go of that laptop. Now, move it in elevation. Watch that.
And we have to make some more.
You can move it forward.
When you multiply up to 47 or 76 gig, this will be a lot mellower. It'll get rid of a lot of little spurs you might have.
Mine just operates at 10 gauge.
5 or 6 dB difference in it. Just raising it up.
On frequency rate.
I mean, it got that much work. Elevation.
You need to go.
Let's go.
Well, you need to be level.
No. I'm saying DD. You need to go.
You need to go left negative.
Yeah.
Like that's better.
Okay.
That's much better.
I'm going in it's all really.
Size of the battery, so you go through, you find the ones that matter. because we don't have the hearse, we have a big bag purchase in, China weapons. Actually, majority of there's a sort of special items there. It's actually, the circuit was originally developed by Dave Robinson, the WA2R. Not part of, you know. So she was like, yeah. From coming there. It's why. It's almost hard to look at networking lines of other things.
So it's a lot easier sound in your ears. And you looking at it.
Yeah, he's had initial words, put it off the ground and.
And the other thing that's kind of unpredictable here is how many reflections there are. And you're off of everything. But the direct look right through the office window looks like it's the strongest signal. Yeah, the bug spring. That's true. I didn't see that.
Oops. Say.
Well, lost.
Well, when I saw you get it as the signal is strong at 9, -9. That's it. It's Al got 9.0. So right, we didn't get it. That's -9. -9. 9 below the loudest it could be. All right.
9.9 is like.
Okay. Now I'm going to move it before you guys come up. Just give them a support. Yes, sir. Yeah.
This.
Myself, but where I land. I'm just retired. Still trying to get my. I don't know what it's going to bounce off of, but one of y'all see, it'll be in this general direction. It's the third row from the bottom, David.
Yeah.
Because it's printing 3 at a time.
Yeah. I see carrier comes up.
Yeah. -9. Looks pretty good.
9.6, 9.5.
Hey, Steve, while they're doing that, you want to talk about your box? Show us your box. You can set it up here if you want, or you can set it up over there.
6.9.
You got a 6.9?
Yeah. Okay.
Well,
There's a 6.6.
it's definitely better than going through glass over there, isn't it? For you, I'm going to move you further.
It switches from carrier to Q60.
That's when it's real monitoring the real beacon.
Gotcha.
This is just a weak signal.
So point -6.1.
Good.
Good. Yeah. Yeah. Okay.
Your turn. You want to move? This one runs off. I also want to try. Mike, this one. Yeah, sure. Go ahead and play with it.
6.1, that's the lowest, right? 6.0. It's that number. So there's two numbers there and that thing.
started thinking about raising the transverter up on pole. You want to put that elevated off the board. If he has to run up to the hole or up that. Put it in the box and you can do the. It lines up to this is it.
You have
Put everything in
the bomb. There's some old stuff.
Yeah.
You send it over to me. I'll build one. I'll buy and build one.
Yeah, I was, see, I think I,
Tons of eyes laying around. I probably have a couple dongles here. I know that's it. The bias to me.
Sure.
People will ditch like that, but I'm sure I can find it.
yeah, any old surplus dish will be okay.
I've got smaller. On this line, mate.
That up.
Yeah, that'll work good.
If I get it set up, I'm happy to help anybody else. Pretty good. Other people set me up so much.
I have these two boxes stacked.
Don't have a day job anymore, so I got a dollar on it.
Oh, yeah, that's right, you retired.
I just retired, yeah.
Yeah.
Last week.
8 gigs, I don't.
So that's a larger size. Probably needs about, you're looking 9.5.
Yeah.
So what's it send? Does it send the WAV file or I can send in the without?
That is in,
No, I know, from this to the internet.
oh, that's, it's sending all of those columns. And in fact, one of them that's not showing its location, so it's one of the shell script options. So you would actually put your location in when you either create your own shell script.
Yes, is a plug in the Raspberry Pi. $19. You can plug a USB GPS dongle, they're $19. And it would read the GPS signal.
Yeah, but that wouldn't make it log.
No, it would, but it would tell you the exact location. The beacon.
Oh, yeah, it would take that. Yeah.
That's the value.
Yeah, not, I mean, we're trying to keep the costs down.
Yeah.
So,
Understand.
yeah, I built it as just a string that you input and you could
Just put in your
put in whatever you want, but I think we'll want it to be standardized to be your call sign and your grid square.
Yeah.
And then when the sends it to the API, that's what we'll have. We'll have that standardized across all the people that have one.
Okay. Like I said, the GPS dongle. I think it's the next expensive one's $19. The cheaper one's in there. It's a USB stick, little short stick goes in the USB Raspberry Pi. It'll work great.
Okay, let's shut down this R5 then.
Good stuff.
Yeah.
Lord willing. Sooner, if it happens.
There's a lot of guys working on that 24 gig rate project that uses better than you get that out. I don't. That's not gonna be our.
I thought it's next size, but it would work with you.
All right, guys, we still have a few minutes left before we're done. We have still some people online. Well, let's go ahead and finish up, and we'll start with a demonstration. So what you're seeing on the screen here is the graphic layout of the demo, and what we're going to show is the reception of two 47 gigahertz beacons. They each have different call signs. One of them is on a tower outdoors about 100 feet away, and one is indoor on the bench. And there is a 47 gigahertz transverter that has a 144 megahertz IF, and that IF signal is going to be split. It's going to be split one direction going to an ICOM 705 that's in USB digital mode, and a CAT cable from that 705 is attached to a laptop running WSJT. The other 144 megahertz IF signal route drops down into the SDR RPI. In other words, an SDR unit that is going to process the 144 megahertz signal, and the Raspberry Pi is going to report it via Wi-Fi. So the laptop on the far left is also connected to the Wi-Fi, and it will show in a terminal window what the Raspberry Pi is seeing. So what this accomplishes is really just showing two beacon signals in one band on the beacon monitor, which is the bottom section. That's the Raspberry Pi and the SDR. Now, the two signals are intentionally close together. I control the frequency by programming it, so I intentionally made them close together for a completely different purpose than this demonstration. But I wanted two signals very close together in order to check the linearity of the gain stages, and that is not covered in today's presentation. One last time, here are the two 47 gig beacons. The one on the left transmitting at .359, and the one on the right transmitting at 353. Now, I'm not sure how well this audio will play, so let's just see how well it does. If not, I'll just narrate this. This is the laptop showing the WSJT signal being received, and in the lower left, this is the beacon monitor, and it will show two frequencies where a beacon signal is being detected. And here we go. Let's see if the audio plays through here. Yeah, not hearing it. So I'll just narrate here, and we won't take too long on this. I might fast forward this. But anyway, you can see now, those of you that didn't get to come up here and play with this, you can see on the lower left 3 rows being stamped out every few seconds, and there are 2 of them that have relatively strong signals showing. A third one apparently is a spur, or it's just pure noise. And you'll see the WSJT waterfall showing very, very strong signal, and it's in the odd minute right now at 1733, and that's why you see just a steady orange blob there coming down the waterfall, because that is the carrier portion of the transmission. And then as it rotates over the top of the minute and we get into the even minute, now we're transmitting WSJT. And the rows that are getting stamped out in the lower left show Q65 as the mode. This is not being detected by the beacon monitor per se, like through demodulation. It just knows from the time that it's exactly the time of the world for the WSJT period to be transmitted by this beacon. This is the outdoor beacon that's transmitting at this time. Now, coming up on the decode, on a 60-second period, we'll get decode around 56 or 57. There's the decode, and it printed. And then I'm going to fast forward here because what we're going to do is change the frequency to 353. Now this is the indoor beacon, 353, and you just see pretty much the same thing. We still have the beacon monitor reporting the original strengths because it's not tied to WSJT. It's got its own split off input, and you can't read this, but the signal strengths are minus 12 and minus 23, so they're about 10 dB apart. And there's the decode W5LUA/B. So there's that. This is the shell script that we're looking at. This is for the beacon monitor itself. As I was telling David, there's a place where you can input your location where this beacon monitor is located. We would pre-configure this for a volunteer station so that they aren't having to come in here and know Linux and change these script files. But for those of you that are comfortable with this, this is where it's located. The frequency is the IF frequency from whatever the input is. In this case, if it's this cheap L&B, the IF frequency is 618 dot some change megahertz. The LO serves no real purpose, it's just notational, but the local oscillator in these units is 9.75 gigahertz. Then here's that gain value that we talked about that can be specific. The threshold above which we want the monitor to note the signal was above the threshold. And we could actually say, don't show us anything if it's below the threshold. So threshold is a value that it will dynamically implement at the time of the monitoring. The interval is how often. Is it like this one, 2 seconds? Or is it once an hour? Or once every minute? 10 minutes? Max signals is how many signals should I find in my sweep. The span is how many kilohertz either side of whatever I put up here in frequency. How many kilohertz either side should I sweep of that frequency? And then output is the name of the output file. If you want one, in normal operation we will want one because the reporter, which is a different Python script, will pick up the data that's being written and ship it or forward it up to the NTMS database. Here's the same thing. You know, you can go back and look at this if you care to, but this is an explanation again like I just gave verbally. Here's one of the actual logs, and you can see the strongest to weakest signal reported. Here's the Excel log. Here you see the location column for the first time. That's not actually output on the screen when you're doing a screen monitor, but it is written to the CSV file. The actual frequency that we know these signals were on is printed here. The IF frequency can be a little bit off because the LMB is not that accurate. If you want to transfer that beacon log, this is a Raspberry Pi-ish kind of thing to know. You go to like a PowerShell session on Windows and issue this command. SCP user at Raspberry Pi 2.local, and then you give the path to where it's located on the Pi, and then you give the path where you want it written on the Windows machine. and it pulls it over. So this is one way, you got to know these diagnostic things if you're going to build one of these, and you want to tinker with one as a hobbyist. You got to know these things. Might love to know these things. Here's how it sweeps. Left to right, low to high. In this case, the frequency input was 360, and I think I had it set to sweep 100 kilohertz on either side. Is that right? No, 100 kilohertz total, so 50 kilohertz either side. So the sweep would start at 310 and stop at 410. That's 50 plus 50, that's 100. Okay, but it's 50 either side. So, and here's the two frequencies that we're interested in. The indoor beacon and the outdoor beacon are right here. They're above the threshold, which was programmed to be minus 50. If you looked at those, when I breezed through them real quickly, you would have seen the threshold is set for minus 50. So is it on this one that you were playing with. That's why you were seeing minus 47s. They're above the threshold. They're stronger than the threshold. And here's all the technical way that it does this. I'm not going to read this. But there is one interesting thing here that we suppress on either side of a signal. That's a value. It's not one you can control. It's hard-coded in the script. It's 5 kilohertz. So it's 2.5 kilohertz either side of a signal. It finds a signal and says, I'm fixing to skirt you with 5 kilohertz filter. It's a digital filter, but it goes boom. It's just an FFT. It looks like that graph in memory, and it just chops everything off 2.5 and 2.5. In fact, I wanted to draw that so that you could see that your ICOM 705 and 7300 and all your modern SDR-based receivers, they can notch it that well. There's some decodes from the demo, 2 different frequencies, 359, 353. And here, we're getting nearly done here. I wanted to just go through, because it took me a whole day or two to do this, but if you just drive out and see how these signals look using this device and using your rover equipment, you come back with more information. Cool stuff. So we'll look at the estimated coverage versus what we observed. The estimated coverage I computed in Radio Mobile. This is a pretty accurate tool. We also have this on the W5 ISP site. It needs some tuning there, but this tool is much more mature. It's been around a long time. It's by Victor Echo 2 Delta Bravo Echo. And then we'll look at some propagation predictions, because in the middle of all of this, the last 2 weeks, Steve can testify, Al could certainly testify, we had an enhancement one day, and it was June the 30th. And we knew about it on June 29th because of Graham's work on the W5 ISP propagation tool and our work with AI and perfecting those algorithms. We were aware that we were about to get enhanced propagation, and we did get it. Unfortunately, we only got it for 4 or 5 hours, and then it was gone. All right, so I first wanted to just start off with the Denton beacon, because everybody knows this is the granddaddy standard, and you'll see that this thing extends. The green print here is going to be detectable 100% of the time, is basically what it means. And you have to input not only the metrics of the beacon, 285 feet, 1.5 watts, omnidirectional antenna, 20 slots. You got to give it all that. But you also need to tell it what the receivers have. And in this case, you only put one metric. So I said, I want the beacon coverage from the Denton 10 gigahertz to stations that have a 30-foot high, 30 dB dish. They didn't ask me for noise figure or bandwidth or any of that, but this is made for really predicting coverage from a base station at microwave to mobile car moving around on microwave. I don't think they could use 10 gigahertz for the Doppler, but it does extend to 10 gigahertz. So anyway, getting back to this, you see the green goes up here well past, that's Sherman in the upper, like 1 o'clock. That's Sherman. And then we're all the way to Greenville at 3 o'clock. And then at 6 o'clock, it's Burleson, maybe Alvarado. And then out to the west is Weatherford at 9 o'clock. So that's Denton. And then the next yellow is observable 10% of the time. So it's a pretty big drop. You might hear it out at this yellow level. So here is the beacon at my house. And these were the normal conditions June 26th and June 27th. In fact, I printed this, made this slide back at that on those days. I did not know we were yet going to have good conditions, and I just said I got to start work on this. And at this time, Al had already decoded the beacon at minus 21 in normal conditions. So that red line shows how far outside the coverage area that Al is at, and really speaks to an excellent station, well balanced system, has good noise level or low noise level and flat noise response. Those are very important. They would become very important even more as we went on. The other little red marks, this is where I drove to. I was reading the beacon at the weakest point down here at the bottom at 5:30. I had a minus 17 decode, continuous decodes there at nearly 50 kilometers. But that was WSJT because the thing does transmit WSJT. Then on June 30th, we got this. At 4:45 a.m. in the morning, we said, show us what's it going to look like at 8:45 in the morning. And it had this. This is the ducting prediction. And it hardly ever looks like this. This is good. This is call your buddy. This is make everybody aware that cares to know. Because we're seeing patchy. It could be that it would be all green if every single station was reporting here. And it's not stations, it's actually high resolution rapid response data. And some of it might be missing. I can't tell. We don't have a missing marker on here. But I like what I see, because when it looks like this, in the past, it's usually done something good for us. Then another way to look at this is the inversion map. This is at the same time. Again, it's on June 30th before 5 a.m. And I'm saying, what's it going to look like 4 hours from now? And I see some green in here, which this green is kind of just coming from the very same map that we just looked at. It kind of looks like, well, that's going to cause the inversion. And then this is the inversion base. So the height above ground where the inversion would be. And the one on the left is 4 hours. Show me what it's going to look like 4 hours from now. And the one on the right is 5 hours from now. So there is a better picture on the left, because you've got more green. You indicate that it's on the ground, it's 0 meters, or it's 500 meters. So there's a blend. And then it begins to deteriorate by 10 p.m. Okay, so this is what we're looking at. The troops rallied, and here's what actually happened. Steve, sitting right there, he detects the Denton beacon all the way across all of this distance. I'd say that's almost 200 kilometers. He's here in the Denton beacon, detecting it. He's also detecting my beacon. And Al is getting a decode now at minus 18. In support of that, let's see, I looked at the skew T-plot. This is on our old algorithm that we have out there, and there were multiple ducks. And we also had a very high refractivity number. I won't bore you with all that, but there's multiple ducks. This green line shows them most pronounced. There's, you see all the wiggles, kind of two noses sticking out to the left. And then something I've learned to do with Graham's tools is when I want to see a real strict analysis of what's taken place, I go log it as if it were a contact in the database. And in here I said, log a contact between Al and the beacon location. Just pretend it's a contact. And when I did that, it began to unfold. This took a few minutes. It takes a few minutes to go gather the data. But it began to have statements like, path is terrain obstructed, but signal likely propagated by atmospheric ducting. A sounding detected layer at 2,480 feet, bending over terrain obstruction, etc. Further down the page, propagation mechanism, it was declared to be tropospheric duct. Further down the page, some of the surface observations, and the profile up here at the very top says ducting. It's also got these other numbers that we've come to understand. One of them is the delta, the dN over dH. This is the delta in two numbers, but when it's right here, it printed minus 159. 157 is the golden number. If you get more negative than minus 157, it's almost confirmed positively to be a duct. And that's what it was. So I ran just a little delta here between the two paths, and they were very similar. The thing I wanted to point out here is the one on the right, which is Steve's. Steve's observations were 2 hours earlier. So at 1200 UTC, he's out in the pasture with his rover rig set up in the back of his pickup truck looking for the beacon. And at that time, the duct layer is 2,900 to 4,400 feet. Note that 2 hours later, it has dropped down. And also this dN over dH number went from minus 152 to minus 159. Boundary layer got deeper, which is that protective, I would like to think of it as the skin over the earth. It's the layer that touches the earth. It got thicker, and that's good, in my book anyway, because that will preserve what's above it better from wind and turbulence. And then the common volume, which is a new number for me, you might be able to guess what that is. And heavy rain pixels, this is another element that Graham is pulling down. Looks like there was more moisture. There weren't rainstorms, so it doesn't mean that. If you Google that, you'll find out more. But 15 rain pixels indicates definitely more observable moisture. And so he had 5 times as much at 1200 UTC as Al had at 1400 UTC, which I think is what we've heard all day today. Al talking about time of day, moisture tending to go from moist to dry. Finally, I wanted to show, this is yesterday, I took this beacon monitor and I set it out in the driveway, and it registered minus 5.7. And Ron, pointing it from there to the weak signal source over there on the floor, got a minus 6. So even though that weak signal source is only running milliwatts, the beacon in my front yard registered like this. It also had a high noise level, which I thought was interesting. So the presence of that strong signal there is raising the noise around the signal. I've got the actual distances and frequency, how many kilohertz away it was. But just suffice it to say, it's just like looking at a spectrum analyzer when you've got a strong signal and you see that the noise skirt is up. I turned off the beacons and it went down to minus 47. So shifted almost 15 dB lower, the noise. Then I went 8.5 kilometers away. There's a high spot between these two houses. There's a driveway, and no, it's not a driveway, it's a road. And I can park there and almost see, where I'm located over there across Burleson. And you're about 100 feet above the ground. Anyway, here's the plot down here. It's about 100 feet. This is not a curved earth plot. This is just a flat earth plot, but you can see it's line of sight. And at that point, my signal strength was minus 27. Now, I can't explain this. I've got to go back because I spent a long time there until I got hot in the sun. But for some reason, when I went out to 28 kilometers, the signal was 9 dB stronger. I don't know why. That bottom plot is down here. JPS Hospital is on the right side, and mine is on the left side. And this is, again, almost perfectly line of sight across these 28 kilometers. Once you factor in the height of the parking garage level and the tower outside. So why it was higher, I'm not sure. I mean, I really spent a long time at that 8.5 kilometer point. I did the elevation. I found some peaks. I found some dips, like the 3 dB dips that you would expect, but I ended up level. I have a level, a torpedo level, and I put it on there and I said, damn, that thing is level, and I'm reading minus 27. I really thought it should be stronger. In fact, I was thinking as I drove to JPS, I'm not even going to hear a thing at JPS. It's minus 27 here, 8.5 kilometers away. But then I was completely flipped upside down and had a good strong signal at JPS. Peaked up real well. There was no doubt that was the signal. Here's the actual, the way that they looked. There's, again, the 1, 2, 3, just like what you were seeing here. There's the minus 5, that's when I'm right next to it, and the signal, the noise level is minus 33. Here it is at the 8.5 kilometers, minus 27. Noise is back down to normal, minus 47. And then here I am at JPS 28 kilometers away, minus 18. That's a very strong signal. Here's some next steps. We're just going to deploy these beacon monitors. We plan right now, there's a couple of you have expressed interest in maybe having one at your location. Right now we know that Paul Perryman will take one in Arlington, and then Graham plans to put one up as well. I'm going to build the high stability beacon so that we can get Q65D codes, just so that's a proof of concept. We have some guys at Texas A&M that are interested in that one. We've got a PSK reporter feed issue. This is a conundrum, and it's tangled up with the way that the RF0 is configured. That software will need some modification depending on what direction we go. And we know that we're restricted with the RF0 to 13 characters in the WSJT string, so I plan to expand that. HAM-SCI. This is the University of Scranton, PA, and they have a beacon receive project for these bands up here, 144, 432, 902, and 1296. And their infrastructure is shown here. It looks pretty familiar. And then the description is here. These folks reached out. We've begun to collaborate, and I gave them some advice on antennas and which beacons in the Pennsylvania area, what would probably be the best way to go about that. For future meetings, I'm not going to get into this meeting, but we know that the CW carrier, let me flip forward, this trace, smudge, streak, whatever you want to call it, this is the CW carrier, and it is visible before decodes occur. We've measured this with tools. It is exactly 2.1 dB signal to noise. It's weak. We want to understand that a little bit better and confirm those tests and do them some more. And when I say it is exactly 2.1, it was in the cases that we analyzed. We want to take the decode threshold apart a little bit more than we already have and understand it. There's a particular aspect of noise and noise color that we need to get in a lab setting. What do we do, guys, when we're working on a problem? We take it into the shop, we get it on a bench, we fire up all our tools, and we start using those tools. And we try to figure out, by process of elimination and all the experience that we have, what our problem is. Well, it's the same thing here. Exactly the same thing here. We want to tweak the receive chain. That's going to be the difference between the LNB and the SDR. In the process, we've created two sets of tools. The first one is called Q65 Toolkit. This creates synthetic Q65 files of any flavor and size that you want. And then we've got something called Q65 Analysis. This performs analysis. We have been able to ascertain that the beacon, not a QSO, a beacon decode limit is about minus 27 or minus 28. The beacon message cannot enter the AP pipeline because of its structure. And then there's some highlighted. The thing to pull out here is they didn't put this chart in the latest WSJT startup guide. I'm kind of glad they didn't, because it's confusing, because it's misleading to me. Because if you don't read it real close, you got to stop when it says yielding 50% probability of decodes. We're really locked into a binary world and society. It's like, well, it didn't decode. Well, did you try it 100 times? No, that doesn't make sense. But when you get it in a lab setting and you run it 100 times and you jack with the color of the noise, you get some results. You get some interesting things begin to happen. But in their given chart, on the 60-second TR period, it clearly says without AP, which is where the beacon has to live, it cannot go through the AP pipeline. 27.6 gives you 50% decode. So I says, I should be able to prove that. Well, we did. And so this was just a graph that showed what kind of a noise depth improvement we had to have in order to get a higher probability of decode at 26, 27, and 28. We only had to do a 2 dB improvement on the color of the noise. I'll let you ponder that, Eric, and all you noise aficionados. Color of the noise to get 50% decode at minus 27. That means 50 out of 100. Okay, 5 out of 10. And this all got started because Al said, I just decoded minus 27 blind decode on the beacon. And we went, what? You did what? So it challenged quite a bit of what we had theorized up to that point until we started playing with this factor, which was the noise, and it was the only thing left to play with. And we learned that in the lab setting, the Gaussian noise, it'll never be the same as real noise and real propagation effects of fading and whatever those strange things are that happen. Here's another slide about why the AP adds 3 dB does not apply here. Talks about the message types. And here's the 2 dB improvement. I like this slide because the broadband noise improvement across the bottom goes from 0 to 1 to 2 to 3 dB. And here's the decode rate percentage going up to 100%. And Al's dB, 27 dB, fell right into this range. Right on that edge. Okay, and then optimizing the receive train. We're going to talk about that next month or month after. Here's some Q65 toolkit stuff for you guys that care. The usage down here to the Python script is you pass in the AP values if you know them. The encoding values. Now, so this is what you want the WAV file transmitted, synthetic transmitted file to encode. So in this case, we said encode W5HN/B EM12IL. You put in the sub mode that you want used. You input the signal to noise ratio that you want. This one has -18. And then you have an F0 value and the name of the file. Now, down here, we've added these other elements to where we can input a drift factor, where it starts, where it ends, in terms of percentage of signal width, the spread. Drift. That's literally frequency. The spread is the width. What's the minimum? What's the maximum? How many times should it change in the period? That would simulate rain scatter. The fade mode, if it's varying, in other words, if you don't put in anything here, it doesn't fade. It just is a steady signal all the way. If you say varying, then you have to also indicate the fade range in dB. And you also have to indicate the time scale. How spread out is it? Is it compressed? Does it happen uniformly, uniform frequency through the period? So all of these perturbations are meant to build synthetic files that can give us testability in a lab setting to find, if there, I don't think we're going to find anything that the Q65 developers and designers haven't already found. But I think what it does is it gives us confirmation, and it shows us everything that we don't care about, and then we care about what's left over, and that's where we focus. Here's the analysis side. This will work. You can set this up to do a batch of files. So Steve sent me the most. Steve gave me a thumb drive with 30 files on it. I just loaded them into a directory and I ran the batch file processor. It also has the ability to do what we call deep dig. This is where it will go many repetitions deeper to try to decode the data that's there. You can take the WAV files from the synthetic builder, or you can take them from somebody that's recorded them over the air. He sent me the ones recorded between him and Scott over the air. Yeah, and the first thing you do is you just run them through the batch decoder without any options, and then you look at the screenshot that he sent of his contact with Scott, and it's a perfect match. Yeah. Boom, boom, boom. Everything that decoded in WSJT decoded, and it should, because we're using JT9XE. So it should just be like replaying them in WSJT. But then that deep dig, because there's some that don't decode. So we want to look at the spectra power levels that are there and the ones that aren't there to understand, well, how close was it.
Some of the deep.
You talking about with version 3?
Yeah.
Yeah. Okay, I just got that. Well, I really don't like being down in this vortex too much. You want to know the truth? It is addictive.
Very good.
And that's why it's like a bad drug drug habit. It's like I really don't want to be there. By the same token, there's unanswered things, and I really would like to be able to know why this or why that. Here's the big picture. The big picture is there's only 3 or 3.5 beacons in the United States of America that transmit WSJT. All the rest, I agree we need more. And in fact, the 3 or 4 that we have now are in large part for the effort of NTMS. And the fact that we did it first. But not everybody's going to run out and rebuild their beacon to send WSJT. So there's this lopsided, most of the beacons are CW. Beacon monitors will work real well with that. They could be low cost. They don't have to decode WSJT yet. And we can build them. And we can make them available to people that will use them. That's where our gap in information is, but I don't think we should downplay somebody that wants a 1296 monitor, or a 432 monitor, or a multiple of several that want to study propagation again at those frequencies. I don't think we want to overlook those possibilities that exist there too. They're just our younger, I want to say younger brothers, there are younger frequencies. They're just when those things start to get good, those frequencies start to get good, many times we start to benefit. It starts hitting us up at 10 gig. So we now will look at propagation tools that tell us how propagation is working at lower frequencies. We look at them now at microwave too, because we have the tools. But we have always looked at the Hepburn. We've always looked at the other tools to tell us what the possibilities are, and those are based on APRS, some of them. So they're tracking 2 meter, propagation. How many times over the years have we seen something work really well? I mean, we see the band starting to open, and it continues to open. It just keeps on, and pretty soon we're at microwave. I can't say enough about the NTMS, W5 ISP tools. They are paving the way for something great. And the more that those tools can be calibrated, and we can't calibrate it with data, without getting data. And so the more, the better. And I would really, the vision I think that we should have is that there will be a lot of these monitors in a lot of different locations, and they will input their data, and we will all of us will benefit. Those local areas will benefit. That's what I told the people at Scranton, is when you send those inputs, you can either compile them yourselves and invent that wheel. That's fine. There's an exercise to that. Might be the curriculum for a whole semester. But we already did it. So if you input those data into our tool and then observe your area with our tool, you're getting direct feedback for your work that you did, your contributions that you gave. And so if that catches on, we'll all end up benefiting. What I wouldn't like to have happen is that it's 2 or 3 of us taking care of all those beacon monitors. We're getting calls every day. My beacon monitor went down. What happened? I took a lightning strike. Is the SD card corrupted? So I don't know what we're going to get into that away, but I think we just have to start and see how it goes. We're not the only smart people. There's going to be other people that can deal with our Raspberry Pi problems, and we might end up having to put solid-state drives on them or something that's more resilient than the little plastic SD card. I do worry about the SD card a little bit. that's all I got. There's some links here that will pull up those videos. They're pretty boring, but they're out there. And that's it. We're going to Central States this week, several of us, so looking forward to seeing you up there, and time to relax and see each other again and measure antennas and measure preamps and all that good stuff. Any other comments before we shut down? Thank you. All right. Well, I guess that's a wrap, folks. Thank you for checking in with us, and we will see you. Pat, we'll see you early this week. Yeah.
Looking forward to it, Jim.
Yeah, me too. And Steve, he's in the audience here too. So we'll send you an email and get our meeting set up.
All right. Sounds good.
Thank you. Thanks, Charlie Osborne. I see you in there, and Tony, Emmanuel, all the steady regulars. Mark, Charlie, Ross is in there. K5ZMJ. Oh, I get to see some of you guys at Central States. All right, guys, I'm going to shut her down. Thank you.